before I share, I just want to tell you that this second half of the course is essentially meant to supplement what has been taught in the first half. The first half, you've been taught some spectroscopy, particularly in reference to organic compounds. Fairly small molecules, fairly simple molecules. Even if they are big, they have only elements like carbon, nitrogen, oxygen. So the number of techniques what organic chemists use are rather limited to, or is sufficient, I would say, to infrared, NMR, and mass spectrometry by and large. On the top of this, you add X-ray crystallography. I think they are done with most of the characterization. But inorganic chemistry, on the other hand, has metals of different blocks, D block, F block, and P block, and they are very different from your carbon and hydrogen, what you see in organic compounds. As a result, what happens is that share screen broadcast. Yeah, is the screen visible now?
Yes, sir.
Yes, sir.
Okay, okay. So I was just talking about the spectroscopy for inorganic compounds is somewhat from the organic compounds, but essentially it's the same because in addition to the organic ligands, the only thing you add extra is here is the metals. So metal bring a few extra possibilities to characterize them. So as I said, it is essentially an extension of the first part of the course, and we have divided the second half of the course into two parts. One is that one deals with the non-paramagnetic molecules, which I will be doing a bit of NMR, bit of IR, and a bit of mass spectrometry. And 3 weeks or 3.5 weeks from now, Professor Lahiri will start and talk to you regarding the the paramagnetic part, namely EPR and magnetism, things like that. Okay, so and those of you who have taken 438 with me already have some exposure to non-proton, non-carbon NMR. So I will be doing a bit more of what I have already done in 438. For others, because this particular class, I think, has people also from the fresh PhD batch. So for them, I think the heteronuclear NMR will be something new. So I last night I sat and kind of scanned through all the slides of Professor Kulkarni, especially the introductory slides, and I see that from his slides that both for infrared and NMR spectroscopy, he has given good conceptual introduction. I can see that I think he has talked about force constant, the springs, vibrational frequencies, selection rules. Same thing about the NMR, about the frequency, spinning top. So I will not be, in fact, touching upon any of these things which have been already covered because it doesn't change too much from organic to inorganic, these spectroscopies. So the concepts are essentially same as that of what has been taught by Professor Kulkarni. I will only start doing from the next class onwards examples. There may be integrated examples. I would be taking up case studies rather than teaching them technique by technique. I'll probably take a case of a cis-trans isomerism in a metal complex and will show you how you use a combination of spectroscopy to solve which of the isomers is in the box or which is the isomer is in the flask, rather than giving a complex and giving a technique and ask you to predict the spectrum. Okay, so as I said, I will try to solve some problems straight away from the concepts. And before I do that, I will just give a small primer to the physical methods in inorganic chemistry, because this word physical methods in inorganic chemistry is much more beyond spectroscopy. Okay, spectroscopy is something where we deal with the interaction of light with matter. So essentially use the entire electromagnetic spectrum from X-rays to radio waves and anything in between, and shine any one of these radiation on the molecule and try and see what changes these molecules go through, and study their exit state, study their relaxation behavior, and get some signatures and say that this is what we have. Apart from these spectroscopy techniques, there are simple techniques what one can use, because uh, at least until the 1970s and 80s, spectroscopy was considered to be only for the empowered people, people who are, having the luxury of having spectrometers in the lab. NMRs were not common until the late 80s or early 90s. Infrareds were not common until the 70s. So these, machines started to come only, and the chemistry is about, 250, 300 years old as far as synthesis is concerned. Ever since the time Friedrich Wöhler synthesized urea, people have been characterizing molecules and compounds without even having these spectroscopies, which were introduced into chemistry or into characterization only in the second part of the 20th century. So as a result, I think I just want to quickly recap, I think, what people have been doing in the earlier times to characterize compounds, because spectroscopy is important. It's much more information full, but even then I think we just quickly revisit. So let's say I'm a synthetic chemist. I think let me just give you a small example. I do a very simple reaction. I take titanium tetrachloride, which is a colorless liquid. It is a colorless liquid. Am I audible and am I clear?
Yes, Professor.
Yes, sir. Everything's
Okay. 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 I'm taking this colorless, liquid titanium tetrachloride and react with one equivalent of cyclopentadiene lithium. 1:1 reaction I do, and I get rid of lithium chloride and make this compound. So this is what the intended synthesis. I want to do something else with this later. But the first step of my reaction is this. I have to know whether this product is formed. Even before laying my hands on a nearby spectrophotometer or spectrometer, can I do some simple things in the laboratory and know whether the reaction is gone? Many things I can do. I will just come to that in a minute. I just show, do I have this product in the flask or not is the question I ask. And I can see there are easier techniques than spectroscopic techniques, which can kind of guide me whether to take this sample to the spectrometer or just wash off the flask and redo the reaction. And another reaction is a simpler one, which probably you have done before the lockdown started. Especially the BS students, I'm not sure, maybe even the MS students. Did you do this synthesis? Maybe yes, maybe not. Making ferrocin. Yes or no? One can
Yes, sir.
unmute and tell.
Yes.
You have done the
Yes,
reaction.
sir.
You may not have followed the same procedure what I showed here. You may use the cracked CP with triethylamine or something like that. But this is another way of making this. I have iron dichloride or ferrous chloride, and I react with the sodium CP, two equivalents, and I get a ferrocin. How do you know that this reaction has really happened? I have the compound, okay? And some more reactions in the next slide, like the preparation of very simple compounds like zinc acetate and copper acetate. Much of these compounds, which are very common, which are not new, somebody else has already made and documented the physical properties of these compounds in the textbooks and journals. One does not have to, rely on spectroscopic techniques alone. One can do simple things. The simple things what people do are the analytical techniques. Okay, so I do spectroscopy for each and every compound I make in the laboratory, or I use any other technique, often simpler ones, which would be available within the laboratory. We do not have to go to the NMR room or IR room. So essentially, this is where I want to introduce analytical methods versus spectroscopic methods in chemistry. As I said a while ago, spectroscopic methods pertain to interaction of light with matter, whereas analytical into analysis, right? Analysis could be a combustion analysis. It should be just looking at the color. It may be just looking at thermal decomposition. So techniques such as color, yield, melting point, thermal analysis are all considered to be analytical techniques. And this analytical techniques, by and large, are much cheaper and much more readily available. So for compounds which have been well documented previously, analytical methods are by and large enough. Only when there's an ambiguity, you run a spectroscopic technique. Okay, that's kind of, I wanted to make it clear. So what I do in the next 10-15 minutes is that I run through some of these analytical methods along with spectroscopic methods. And also I will probably kind of tell you the sequence in which you have to approach this problem of characterization. And how do you really go about characterizing a compound? What is this? Okay, so essentially at the end of the day, we want to know what is the structure. I think Professor Kulkarni would have talked about the importance of three-dimensional structures, absolute configurations, up-down configurations of methyl versus hydrogen groups in chiral molecules. These are very important for chemists because this relates to some activities or otherwise of some of the important pharmaceutical drugs and things like that. I want to know the three-dimensional structure. I just shown some molecule from my lab, which is quite huge, inorganic molecule, which has an inorganic core in the middle, and a lot of organic groups surrounding it, and makes a nice large spherical molecule, whose molecular weight is something like 3,000 plus. Okay, such a big molecule is there. So the questions one would ask depend on this is what we are studying, and also upon the progress of the separation and isolation, and the level of detail what you want to know. Suppose if you are dealing with the reactions that lead to products that have not been made before, we need to ask a series of questions, in fact, serious questions, in order to really characterize them. So, as I said, this series of questions will, of course, increase with the complexity or subtlety. Okay, to start with, we need to ask: does the material consist or contain any compound that we can identify, or is it just some junk? Or is the compound what you have made, or the product what you have made is single compound, or a mixture of many compounds, or a mixture of many isomers? These are the questions you ask to start with. Then you ask some more questions. I'm not going to read this out one by one. So, but there is a level of or the degree of increasing complexity which will give us more and more information. So the kind of questions what you can ask is that what is molecular weight, what is elemental composition? Both these techniques are analytical techniques, determining molecular weight and determining elemental composition. In good old days, people measure the molecular weight of the compounds by density measurements, okay, by ebuloscopic measurements. I'm not going to go and talk about these age-old techniques because they are no longer in practice and nobody has time for those techniques to do that. But the modern molecular weight determination technique, which is an analytical technique, is mass spectrometry. Okay, although we use the word suffix spectrometry, it is an analytical method. Okay, because you ionize an atom or a molecule or a species or a protein, whatever it is, by knocking off a charge or adding a charge and create an ion, and follow this ion by variety of detectors. Okay. Though named as spectroscopy, mass spectrometry is an analytical technique. And elemental composition is nothing but measuring the amount of carbon, hydrogen, nitrogen, metal, phosphorus, so on and so forth, in terms of percentage in a given sample, which is normally done by a combustion analysis. Those of you who walked into the what is called the common instrument room in the second floor next to the department office would have seen an element analyzer where we weigh in and put some 10 milli of the sample, and it is taken inside the furnace automatically, and then it's burnt, and the evolved gases are analyzed, and you get the common percentages. These two are analytical techniques what normally people do beforehand, because they are considered to be rather inexpensive in terms of time as well as in terms of the money that you want us to spend for each sample. Okay, and then I think there are a series of questions you are going to ask: the functional groups, how are the functional groups linked to each other, how they are linked together, what is the three-dimensional shape, planar, non-planar, has high symmetry, low symmetry. And then once you know all this, you really want to know whether there is an electron withdrawing group which is making a bond longer, or an electron donating group which is making a bond shorter. And you actually get into the finer details. You now really look for the finer details in the structure about small variations of bond lengths and bond angles. And then finally, you even do what you call as molecular structure simulations and calculations using ab initio quantum chemical techniques and understand the orbital picture and charges and so on and so forth. So essentially, this is the whole gamut of techniques have before you allows you to understand the structure of a molecule either a little bit or a little bit more or fully depending on what is your need. So you can stop at any point and say that I have known enough about this compound. I rather start using this compound for of my applications rather than digging to know whether the metal to carbon distance is zero point 0.1 angstrom longer or shorter, which is often is not of really concern for a synthetic chemist. But if somebody is using it for a property based application, then these differences become very, very important. Okay, this is kind of this points what one should know, the questions one should ask before even embarking yourself on this exercise of determining structure of compounds. Okay, I'm just going to kind of run through again. I think this is probably repetition. I've already spoken about this. The methods of characterization of inorganic compounds, by which we mean compounds containing a metal, are not very dissimilar to those of what you have learned in organic chemistry. The nature of the compound, of course, precludes some methods, but it also opens up other methods. The following slides is essentially a partial list of different physical methods, what they tell you and what their applicability in characterizing inorganic compounds. Okay, so let me just start with something which is very, very easy. Okay, at least people in military, I think some of them are in the classroom. At least Gargi, who's my TA. I always tell them that when you make a compound, go and look for melting point. Okay, when you make a solid melting point, when you make a liquid, look for a boiling point. Because all of you have been taught about the colligative properties of solids and liquids very early in your education, maybe in the plus one, plus two, or even the first year of your undergraduate program. Normally, pure compounds melt and boil at sharp temperature, whereas impure substances, melt at a temperature range. Suppose let's say I have a compound, acetylene, for example. I don't know what exactly the temperature, maybe 132 degrees centigrade. If I have a pure single crystal, it will melt at the temperature. Suppose it's impure, it has some muck with it. It often melts at temperatures few degrees lower than that of 132. This is that is a colligative property of a solid. Okay, same thing about the boiling point also. Okay, so what we really do is that if a compound is already known and if its melting point is measured by someone, it's reported in a journal or in a thesis or in a book. Why on the earth you run to a high field NMR machine and record its NMR and spend 2 hours to interpret it? Okay, if this tungsten carbonyl with the 4 carbon monoxide and 2 phosphines has a melting point of 175, when somebody has reported, you after making the compound and purifying it, simply put it in a capillary and stick it into a melting point apparatus and heat it up and look for its melting temperature. 175 melts, fine, very good. You have a pure compound. Does not melt 200, 250, you have not made the compound. Okay, something melts below 175, only 5-10 degrees, maybe compound is impure. So the first lessons are learned by simply measuring this. Is an analytical technique, namely melting point and boiling point. No sophisticated spectroscopic technique, what we may teach you, would replace these techniques in a common synthetic lab. People will continue to measure melting points for many years or many decades or many centuries to come, because they give within 5-10 minutes of making the compound an idea about whether you are in the right path of making the compound or you have failed in your reaction. So that's first one. Second one is color. I think this is pretty much very important for inorganic chemists vis-a-vis organic chemists. Because most organic compounds, but for nitro compounds and things like that, azo compounds are colored. The rest are all often colorless or white in color. But inorganic compounds, I think most of them have this MLCT and LMCT, I think, which you probably have heard of, make compounds colored apart from the DD transitions in the metal complexes. So if I quickly go back 2 or 3 slides, titanium Cl4 I said is a colorless liquid. CpLi is again an off-white colorless solid. If I mix this and make this compound, this is an orange solid. already you know that your reaction is gone or not by observing the color. I think the color is not something you can underestimate. Okay, even same thing about ferrocene. Okay, this is you guys know what is the color of this. You have made this. I'm not going to tell you. You better know it. Okay, so the color can give you an idea. Same thing about copper. It's blue in color. Okay, so is copper nitrate, but it's greenish blue. This is blue. Okay, so often color can give you an idea about the reactivity, or the reaction has proceeded to the right products or not. Okay, so that's the second one, very easy one. I already talked about element analysis, uh, and this is again, you can never publish a paper in an organic chemistry or inorganic chemistry journal for a new compound without giving correct element analysis. Because element analysis is not like the fingerprint in IR region, but it's quite unique unless you're talking about isomers of same compound, metaxylene and paraxylene, or cis and trans WCO4 phosphine twice. Okay, the isomers will give rise to the same element analysis, but uh, the element analysis of the products will be significantly different from the starting materials. These are very useful techniques, and any deviation of more than 1% from the calculated values to that of the experimental value by 1% is considered to be an impure sample, and the paper would come back from the journal to you, okay, asking you to recharacterize. Okay, and this is again a cheap technique, as I said. It often does not cost more than 500 rupees for a sample, so this is something you can immediately fall on when you have made a new compound. Okay, moving on. Uh, first, I talked about melting point, what you have in the laboratory. And second one is color. I think you don't need even laboratory. You can see a compound wherever you are. And third one is element analysis, which is not very expensive. But I'm talking about an expensive technique, fairly expensive technique, which is mass spectrometry. The real is for spectroscopy. Okay, we use the word spectroscopy without even it's a misnomer. Okay, so the mass spectroscopy is an often used technique to determine the molecular weight of the compounds. This is very so in organic chemistry, but inorganic chemists have added advantage. Suppose let me say that I have a molecule, I have an aluminum isopropoxide, which is a monomer, and I have the dimer of it. This is just a theoretical example. So apart from the fact that it gives you the molecular weight of the compound, often it tells you the product that is formed, what is the state of this? Because complexes can be monometallic, dimetallic, trimetallic, or can be clusters. Okay, mononuclear, dinuclear, trinuclear compounds you have read of. Like for example, the iron carbonyls. Okay, so molecular weight determination by mass spectrometry has an added advantage. It also can tell you that whether you are dealing with compounds in the unassociated form or an associated form. Okay, if I may switch over quickly to whiteboard. Oh, this is a Netflix I'm opening. Not. So if you can switch over, can you see the screen? Whiteboard. Hello.
Yes, sir.
Sir,
Okay. Okay.
Yes,
Yes,
sir.
sir.
Okay. Now I have a molecule which is an example from my own research. Doesn't matter. What is important is that this particular molecule is a phosphonic acid. If I don't know R, I have an OH, is phosphoric acid. But if I replace the OH by an R group, this is called phosphonic acid. Doesn't matter what it is. Let's say this is R is equal to tertiary butane. Doesn't matter. Has a molecular weight of 100. I'm just saying this is a fictitious number. Number could be something different, 130, 140. 100 is a molecular weight. But what can happen is that this molecule can associate such a way that four such molecules can come together So as you can see, I have drawn these hydroxyl groups and the oxo groups in a concerted fashion so that I can start now drawing hydrogen bonds between them, right? So I can have a large number of hydrogen bonds. So I can have, as a result, weak tetramers, weak hexamers, and so on and so forth. If I have a very soft ionization technique, I don't hit it with the hammer, but I kind of just brush with the painting brush, the molecule. I just do a very soft ionization. Add a proton or remove a proton in a very soft fashion, the clusters remain undisturbed. So I can even study in solution the association behavior of molecules. So mass spectrometry is a bit more beyond for inorganic chemists compared to organic chemists, because apart from taking care of just telling you whether I have aluminum isopropoxide, it can tell me whether it's monomeric or dimeric. You know this in a molecule such as BF3, AlCl3. BF3 is monomeric, AlCl3 is dimeric. So such examples can be easily studied, which are covalently dimeric and covalently tetrameric. But even if they are not covalently dimeric tetrameric, and if they are only held together by weak forces like hydrogen bonds or any other van der Waals forces, even they can be mass spectrometry. So mass spectrometry, in my opinion, an extremely important technique for organic compounds, inorganic compounds, biological compounds, proteins, etc., because it gives a lot of information. And mass spectroscopies are taught for chemistry majors, at a higher level as a full course. I don't think we have the luxury of teaching mass spectrometry as a separate course. So I would encourage any interested person to really look up the various techniques. I see that I think Kulkarni probably talked a little bit about the various fragmentation, not fragmentation, various ionization techniques. Probably yes. If he has not, I think if time permits, let me just talk about it towards this later part of the course. Moving on, spectroscopy. I'm not going to spend much time. I just other than to read out. Here I have not cataloged them as per the energy difference of the ground state and exit state, but rather the ease with which you can measure the spectroscopy. UV visible is a very common technique. Most modern UV visible machines, the benchtop ones, cost a couple of lakh rupees. Okay, the fancy ones about maybe 5 to 6 lakhs. So each one can afford this in their laboratory. So UV visible is a technique where you study electronic transitions. I will come back to that a little later. IR and Raman are complementary techniques which look at the springs vibrating. In the entire organic chemistry discussion, you would have probably learned more about fingerprint region. I will probably take this to a different context and talk about how do you use IR spectroscopy to determine the isomeric forms of complexes. I will take some metal carbonyl complexes. Uh, uh, just one or two of you can unmute and answer this question. CH547 has been taught by my colleague Professor Mathur, right? Did he touch upon application of IR spectroscopy for metal carbonyl complexes?
No, sir.
No, right?
No.
No, he did not talk about how we use group theory applied to IR spectroscopy to solve problems in metal carbonyls. No, right? Okay, I probably will do a class on that. Okay, fine. So, so IR and Raman are very interesting techniques. One involves the just vibrations along directions. Other one is a polarizability. Okay, I probably talk a little bit of this at a little later stage. Raman spectroscopy becomes extremely important for material science rather than inorganic chemistry. People work on carbon nanomaterials, graphenes, and things like nanotubes. Use Raman spectroscopy to a large extent. As you know, Raman himself discovered this, phenomena using diamond, applied to diamond in the initial phases of discovery. So Raman spectroscopy is extremely useful form of vibrational spectroscopy for not so very complex molecules. The Raman spectrum gets much more complex for molecules which have too many atoms. So simple such systems having less functional groups are more amenable for Raman studies, whereas IR can tolerate any size because it's a technique based on fingerprint region 900 to 1500, whatever the region is all about. So we will see some of the interesting examples from the inorganic chemistry part. Okay, then much of the time what we are going to spend is going to be spent on NMR spectroscopy. This is a workhorse of the chemistry. Chemistry, is like a BC and AD. The NMR is okay. Before NMR and after NMR, I think before NMR the chemistry was something different, and after NMR was discovered, the chemistry has changed a lot. Okay, it's a technique which is normally useful only for diamagnetic compounds. Not that you cannot do paramagnetic NMR. Okay, you can do paramagnetic NMR. It's often done in cases where it's necessary. Often applied to proton and carbon, but there are 90 other elements, okay, that have at least one NMR active nucleus. Those of you who are part of my CH438 course would know this. I've introduced at least phosphorus, fluorine, germanium, silicon, and a few other nuclei in the 438. We will probably have a rerun of some of those techniques, but not the same molecules. Okay. I think there are other techniques like a single crystal NMR. This is getting popular by day. I also seen slides of Kulkarni showing you NMR spectrometers then and today. Now the NMR machines have 900 megahertz, 1000 megahertz. So these allow very small samples to be measured very easily. So, for example, you can just mount one small single crystal, okay, and then measure a NMR spectrum and then reduce structure. And magnetism again is a technique which is essentially used to study the paramagnetic species. Again, this will be touched upon by Professor Lagari. So is the next slide, which I will not really talk about it. Okay, so EPR is for paramagnetic compounds with odd number of unpaired electrons. So in this experiment, we irradiate a sample with a microwave radiation. The other one is radio frequency, the microwave, but they are close to each other. And the field is swept across until you see a resonance. The field at which the resonance occurs depends on the number of unpaired electrons and the geometry. Whether it's square pyramid versus TBP, one can easily pick up our copper complexes using EPR. Professor Lagari is an expert in this area. He will talk about this 3 weeks from now. I think mostly he'll be talking to you about EPR, a very, very powerful technique for all paramagnetic species, which cannot be probed by NMR easily. In many ways, I must kind of inform you that NMR and EPR are the same. And even there is a technique by the name ENDAR, okay, which is electron nuclear double resonance spectroscopy, which combines both, NMR and EPR. We do not do this in IIT Bombay, but it's not very difficult to do. I think there is one group in, at least there used to be a group rather in IIT Madras, which used to do a lot of ENDAR spectroscopy. That professor is now retired. I think probably even they don't do it because it's not necessary any longer, because EPRs were uncommon once upon a time. EPR machines were uncommon. Even today, EPR machines are uncommon. Okay, for every 20 NMR machines, you have one EPR machine, even the world production wise. Okay, that's also kind of because organic chemists are outnumbering the inorganic chemists in the world. So within inorganic chemists, there are people like me who do not do paramagnetic species. Okay, so even inorganic chemists use NMR more than the EPR. So the EPR becomes a technique only for people who work with elements like copper 2+, manganese 3+, nickel, and such elements, not with the chromium or tungsten or phosphorus or sulfur or silicon. Okay, I think I have given a kind of bird's overview of all the techniques. I have conspicuously left with one technique, namely X-ray crystallography. I made a slide, but it has not got translated from the computer to iPad. This is the ultimate, okay? If you have seen the last 10, 12 slides and followed it, with me, essentially by every passing slide, I put my sample through, I get more and more information, okay? I get some information at the melting point and some more with the color and some more with the It gets some information with the mask, then with the IR, UV visible, and NMR and APR. If I'm not satisfied with any of these techniques, I still need more information. Give me more. If I need more, give more information. The only technique which I can fall upon in today's context is the X-ray crystallography, because this is the one which actually takes photographs or snapshots of the molecule and gives you a complete three-dimensional picture. These are the is like is a frozen shots of a sprinter. Okay, a sprinter is sprinting a 100-meter dash, and then you use a high-speed lens, and then freeze the shots. Right, something similar to that. X-ray crystallography is like freezing a shot and then taking a picture and then showing it to everyone. What does it give? It gives you the equilibrium bond distances, bond angles, conformations, diagonal angles, electron density distributions, bond critical points, and everything what you want. So, but only problem with X-ray crystallography is that, as the name would suggest, you need crystal. Compounds which do not crystallize are not amenable or not possible to be subjected to this technique. Of course, there are now techniques like called electron microscopy, which are kind of a poor cousins of X-ray crystallography. Poor cousins in terms of the information you receive, very expensive cousins in terms of the money you spend. You spend about 2 crore rupees to get a very good crystallography machine. To get a good electron microscopy, you spend about 30 crores. So when I say poor cousin, I'm not talking about the money you spend. I'm talking about the information what you get. Okay, because electron microscopy probes only surfaces, whereas crystallography actually can dig really deep and information about what is happening deep inside the crystal also. Okay, so these are two different techniques. If you can get a crystal, there's nothing like that. If you don't get crystal, you can still use things like probably you heard of the technique which got a Nobel Prize a few years back called cryo-electron microscopy, which is used nowadays to solve protein structures which do not really crystallize. Protein molecules are really huge; they don't crystallize very well. So, but you have a protein speck. Speck means a dust, a particle. Can you disperse this particle on a in a suitable medium, and look it under the electron microscope, which is the highest possible resolution, and look for atoms, not for the structure, means not the gross structure, not for the shape, but look for the atoms and the the connectivities. So this kind of completes the range of techniques. Morning had a brief discussion with one of you, one in the class, about what Kulkarni on timescales. The answer I got was not much really about. So the timescales become very important, I think, for non-organic molecules or inorganic molecules. It's not that it's not important for organic molecules, but the covalent molecules are much easier to be studied by NMR spectroscopy without much botheration about timescales. But timescales become very important. Timescales means I'm not talking about timescales. Let me see what is a battery stay. Battery is okay, it's doing good. Maybe another 10-15 minutes. Maybe after that my battery would go off. So when I talk about timescales, I think we have to talk about if thing. It's like it's just not one time. There are different times actually. When you're talking about spectroscopic measurement, you have to at least consider 4 different times. It's like the 3 hands of the a watch or a clock. Okay, how all the 3 hands in a watch or a clock is important. Okay, these 4 different times are important. When you really want to talk about time scales of a process. Okay. The conclusion we draw about structures are related to the time scales associated with the processes which we want to really investigate. So it's better that we spend some time and understand these time scales a little bit more. I have listed point 1, 2, 3, 4, these 4 time scales, starting with the time during which a quantum of radiation, normally a photon, can interact with the molecule. I'm going to elaborate each of these, I think, before I close this lecture. I'll go through all these 4 points a little bit more in detail. So I'm just simply cataloging here that there are 4 time scales or 4 times, 4 different times. The first is the time during which the photon can interact with the molecule. This has some definite time. Once you excite this molecule with this radiation or a photon, the molecule goes to the excited state. And how long this molecule can remain in the excited state is the second time. It's called the lifetime. Okay, the lifetime of the excited state is the second time which we all are concerned about. And this is something. The second point and third point are somewhat related, somewhat confusing with each other. But you need to, recognize there's a subtle difference between the two. The second point, you are concerned about the time of the excited state being alive. How long the excited state is intact before it decays back. The third point talks about the amount of minimum time, okay, this lifetime that the sea species being studied for us to see it as a distinct species. If the lifetime is large and if it starts decaying in a particular fashion and does not spend enough time there, that it has to correlate. I mean, it has to correlate with the time that you have in your hand to see it. If suppose the lifetime of the excited is 10 power minus 16 seconds, let's say, for just an example, I'm just telling you, and the probe what you're having is not 10 power minus 16, but 10 power minus 12, they don't match with each other. So I'm talking about minimum excited state lifetime that the species should be studied, should have, to allow it to be seen as a distinct species. This is also important. I will explain this a little bit better later, so you'll understand what I really mean by this. And also at the end of the day, you have to this is the least important one, but you have to be concerned at times about the total time of the experiment. It can be several days in terms of crystallography and other techniques to just a few, femtoseconds to attoseconds in some of the other spectroscopies. Okay, so essentially all these 4 times contribute to different things in the spectroscopy measurements. I will be explaining all these 4 points in detail. So before I do that, what are the time scales of typical molecular processes? Okay, I'm not talking about any of these 4 points right now. Okay, I'm just talking about power has come back. That's a good news. What are the time scales that are typical of molecular processes? Okay, this is important because this allows us to relate them to timescales associated with various spectroscopic techniques. For example, typical vibrational frequencies are in the order of 10 power 13 to 10 power 14 hertz. Okay, you can convert this into centimeter inverse, you will understand it better. But to keep the uniformity in the units, I will be using for this lecture everywhere only hertz. Okay, so the vibrational frequencies are in the order of 10 power 13 to 10 power 14 hertz, while the rotational frequencies are around the order of 10 power 10 to 10 power 12 hertz. Okay, so essentially the rotational plus vibrational scans this space between 10 power 10 and 10 power 14 hertz. Okay, now this is what we know, what vibrational spectroscopy and what rotational spectroscopy can actually have time scales for their processes. But let us look at some of the chemical problems. Let's look at ammonia. Ammonia inversion is something which has been introduced to us at a very early stage. We know that ammonia undergoes tumbling and inverts itself at the rate of about 10 power 11 hertz at room temperature. So ammonia inverts at 10 power 11 hertz. Remove NH3, remove nitrogen and put a phosphorus there. Okay, phosphorus now inverts, okay, at the rate of 10 power 3 hertz. 10 power 9 times slower actually. 10 power is a reduction by 10 power minus 9, 10 power 9. Okay, it's okay. And go to methane. So NH3PH3, I'm going to a highly covalent molecule methane. The inversion rate of methane per molecule is about 10 power minus 16. I should have 8 hertz missing there. 10 power minus 15 hertz. What does it really mean? A molecule of methane would invert from up to down, from normal form to inverted form once in every 100 million years. So methane inverts once in every 100 million years. Okay, And this is an example I taught you in 438, CH438, which is the Berry rotation, the pseudo rotation of PF5 molecules, where it goes from axial to equatorial, where there is a seesaw, conformation which goes from axial to equatorial. So if those who recall your 438 course, remember that, PF3, keeps changing its axial to equatorial positions at a rate of about 10 power 5 hertz at room temperature. There again, I do a small change, move from PF5 to PCL5, the rate of exchange falls to 10 power minus 4 hertz. So what does this all say? This all says that I cannot be using one technique. One size doesn't fit all, or one technique doesn't fit all. I cannot be using one technique. I can study ammonia 10 power 1 hertz using this spectroscopy, namely rotational spectroscopy. I can simply study the inversion of ammonia using rotational spectroscopy. But if I have to study phosphine, I have to look for some other technique. Methane probably you'll never be able to. So here again, I can use NMR here. So essentially, depending on the rates of processes which you want, that's what I said. What are the time scales? What are the time scales of the typical molecular processes actually restrict us or make us to choose the right technique? This is the problem I have in my hand. I will use this technique. Okay. For another problem in the hand, I probably have to go to another floor in the building, to another spectrometer, okay, and use another technique. Sometimes I may even not use a different technique. I simply may use even the time, the temperature of it. I'm not time, the temperature. Sometimes I can change this, rates, the 10 power 1 hertz, 10 power 3 hertz, 10 power minus 15 hertz, or 10 power 5 hertz into something else by cooling or heating the system. Okay, by cooling or heating the system, I can make my tumbling motions either faster or slower, so that I can make another spectroscopy technique which is normally not possible under room temperature to be suitable for this given molecular process, okay, at a different temperature. So these are the gimmicks or the little the games you play around to use different techniques. So this particular slide is essentially to impress you upon that different molecular processes have different times, and you have to look for different spectroscopic techniques. Okay, so I talked about 4 different times 2 slides back. Oh God, this is sorry. Yeah, 4 different times this year. These 4 different times. Let me just in the time that is available. This is the time what I have with me for today's class, which I don't plan to go till 3:30. I probably stop a little earlier than that. Because I want to talk to you. I want you people to unmute and talk to me a bit at the end of the class. These are the slides which are probably not completely done. I will fix these slides. For example, this is 10 power minus 16. This is 10 power minus 19. I wrote them and during the power cut in the iPad, I had to probably correct these things. So, but it doesn't matter. Let me just quickly rush through these 4 different times. The time one is the time during which the quantum of radiation can interact with the molecule. This is the photon hits the molecule and there is an excitation takes place. How much time the photon takes to interact with the molecule. So this is the time essentially taken for photons to pass by the molecule, or sometimes only the relevant part of it. Sometimes you don't want to study the entire, because you do a partial irradiation also, right? So you don't really study the entire molecule, you only see a part of the molecule. So this is the time that is taken for photons to pass by. Okay, you just pass by the functional group or molecule. Sometimes particles used in the diffraction experiments move at rather less than the speed of light, for example, X-rays. But in all cases, we are concerned about interaction times, typically between 10 power minus 16 to 10 power minus 17 seconds. So it's a very, very, very small time. Okay, the photon and the molecule are in contact with each other to the order of only about 10 power minus 16 to 10 power minus 16 seconds, which is sub attosecond time scale. This is what I said. This is very much less than the time taken for molecular vibrations, again spelling mistake, rotations, or rearrangements of light. So what does this mean? This really means that each particle or photon sees the molecule of interest with an instantaneous structure in a fixed electronic, vibronic, or vibrational and rotational state. Something pretty similar to what I said some time ago, a sports photography. Okay, so the photon interacting with molecule is a process that happens in a fixed electronic state Ex, Vx, Rx. Okay, these are three coordinates: Ex, Vx, and Rx. Electronic state, vibronic state, and rotational state. So these three states, are the addresses. X, Y is the coordinates, are the coordinates of the molecule at that point of time. Okay, this is what you're really going to image, either in X-ray or either any other spectroscopy technique. In some of the spectroscopy techniques using electromagnetic radiation, this molecular state is changed. Essentially, molecular state, the ground state is different from the excited state. But in techniques such as NMR or EPR or ESR, it is not the electronic state, but it's a nuclear state which is changed. So in diffraction experiment, there is no equivalent. Okay. So what I'm just trying to say here is that the change is sometimes electronic, sometimes is the nuclear, and sometimes is neither electronic or nuclear. Is simply diffraction, which does not fall into either electronic excitation or a nuclear excitation. Okay. So, but all these techniques help us to know what the molecule we have in the hand. That's about time one. Time two is the lifetime, okay, of the excited state space, during which a quantum of radiation can interact with the molecule. In these processes, okay, I'm talking about the process which I just said before, okay. There is an effective lifetime associated with the conversion of upper excited state into lower state, okay. So the moment I excite something from a lower state to higher state, there's a lifetime which is associated with the excited state before they climb the downhill and come back to the ground state or the lower state. This lifetime is commonly, rechristened or renamed by spectroscopists as a relaxation time. Okay, at least, but the NMR spectroscopists don't use the word lifetime; they use a relaxation time. Okay, in spectroscopy. This is in general short if the energy gap is large. If the energy gap, that is this ground state to excited state, is very large, okay, the lifetime is small. On the other hand, if the gap is small, the lifetime is large. I think you should remember they're inversely related to each other. If the energy gap is large, okay, it just falls off fast, so the lifetime is small. Okay, and these 2 points you must remember. Table form a little later. Thus, relaxation times associated with the low energy techniques. This is a low. I'm sorry. This is a low energy technique. This is EPR. This is NMR, which uses radio frequency and micro radiation. These are very low energy gap. These excited states will have longer lifetimes compared to electronic spectroscopy, vibrational spectroscopy, IR spectroscopy, which have a larger energy gap, which have a short lifetime. This is very important. The lifetimes are, again, the deciding factors of the sharpness of your signals in any given spectrum. If lifetime is large, spectrums are well resolved. If lifetimes are very short, if your excited state is in a hurry to relax very fast, spectrum is a mess. It's very, very broad. I have shown you in the, especially the BS students, I shown you the spectrum of titanium S2O 6 times plus, titanium 3 plus spectroscope, the D1 transition, okay, which is a very broad signal at the wave number, at 23,000 wave numbers, right? It's a very, very broad signal. That is because the energy gap is very high and it falls back very fast. There is an uncertainty. That's what the next slide I'm going to talk about. Okay, this is just, I think this has been seen by you many times. We are talking about low energy and high energy here, and these are intermittent energy. Here you have your NMR, EPR, all these things. Here you have your X-rays and in between you have rotational and IR. Okay, now let us elaborate these points. Larger the gap, shorter the lifetime. Smaller the gap, larger the lifetime. So the time to continues here. When the relaxation times are short, the uncertainty principle comes into play. Okay, it becomes important. If you had to, say that the lifetime tau of an excited state is tau, and the uncertainty energy is the delta E. So uncertainty in energy is delta E. The relaxation time or the lifetime is tau. These two are related to each other by the expression tau times delta E is h cross, not h cross. Okay, so the lifetime times the uncertainty energy is h cross. Okay, so spectra consists of lines that represent transitions. Okay, so I have here, I go up there and then come down here. These transitions are seen as lines in the spectrum. Okay, like this. Okay, so and if the uncertainty in the upper state becomes large, the lines will be broadened and the resolutions will be lost. So if the uncertainty is large in the upper state, if the uncertainty in the upper state is small, then the lines will be very narrow because the resolution is not lost. Okay, so in extreme cases of this line broadening, you may just see a single broad road hump kind of a signal. Okay, there is no feature. There's no feature in the signal. It's just one big road hump. Okay, there's one big road hump, and you do not see any useful information. I will just show how this happens. The constant h cross, as I said, is just hold on for a minute. It will come to just 1 second. I want to switch over from what is it? How do I go about it? Oh God. Just to the oh God, I got locked out, is it? I switched to network, it locked me out. It was switching time. Hello, can you hear me?
Yes, sir.
Yes, sir.
Yeah. No.
Yes,
When I
sir.
switched over from the network,
Yes, sir.
when I switched to network, it disconnected me. Okay, I am fine now. Okay, I go back to start broadcast. I won't take more than 5-10 minutes because I just want to talk about this 4 times and close this lecture today. Okay. Yeah. Because I hate any lecture beyond 1 hour, but they have given us 2.5 hours. I cannot do this otherwise. So, you see my slides again?
No, sir.
No, sir.
No.
No, sir.
Okay, 1 second. Let me see what is the problem. Yes. Start broadcast. Screen broadcast. Now we should okay work with it. Abhi?
Yes, sir.
Okay, good.
Yes, sir.
So you know the value for h cross is 10 power minus 34 joules second. Okay, that's the value. You know this. Okay. Now for electronic spectroscopy in solution, the tau is 10 power minus 15. So tau is 10 power minus 15 into delta E is equal to 10 power 34, 10 power minus 34, right? Right? So what is delta E here? Delta E, sorry. What is delta E now? Delta E would be equal to 10 power minus 19. Okay, so delta E would be 10 power minus 19 joules per molecule. Okay, so for the electronic spectroscopy, since tau times delta E is equal to h cross, 10 power minus 15 into 10 power minus 19 will be 10 power minus 34. So delta E is 10 power minus 19 joules. So that's really huge. Okay, even 10 power minus 19 might look very small number until you see the next point. On the other hand, the NMR, for the NMR, the tau is the lifetime, or the relaxing time is typically 1 second to 100 seconds, and hence delta E typically drops to 10 power minus 34 to 10 power minus 36. So now we are talking about 10 power minus 34 for NMR versus 10 power minus 19 for electronic spectroscopy. This is NMR. This is UV visible spectroscopy. So the difference is about 10 power 15, joules. You know, so if I say that if I multiply this numbers by Avogadro number, okay, I will get this in a per mole. This is for per molecule. Okay, this is 10 power minus 19 is per molecule, joules per molecule. If I multiply by Avogadro number, this 10 power minus 19 will translate to 6 into 10 power minus 14, whereas kilojoules per mole. Whereas for NMR, it will be just 6 into 10 power minus 34. So essentially, the uncertainty in NMR is far smaller than that of UV visible. That's why in NMR signals are like this, whereas the UV visible spectrum is like this. Okay, so the uncertainty is very high. Is this point very clear? I think this is something which I wanted to teach if Professor Kulkarni has not taught. I think this is very important for you to understand why some spectra are broad and why other spectroscopy techniques are narrow. Okay, and how does one get fine structures even otherwise by beating these points. Is this clear? One or two can really unmute and let me know. Hello. Hello.
Yes, sir, it is clear.
Yes, sir.
Yeah, there is no complicated maths here. Okay, it's just that we know the value of h cross, and we know the value for the tau, the lifetime of excited states in the various processes we know. So I'm going to jump to the next slide and point to put these numbers in perspective. The next slide puts the numbers in perspective. This is just sorry for this very poor photography from a book using my cell phone. Okay, but are the numbers visible? Hopefully, it's clear. The numbers.
Yes,
So
sir, it is clear.
it's clear. Okay, right. So now what you have here is I have given the energy of the excited state for various techniques: NMR, ESR, rotational, vibrational, EPR, and Mossbauer. With the increasing energy of the excited state, that means I need more and more energy to excite my molecule to the excited state. Hello, I got logged out. Hello,
Yes, sir.
sorry, I got logged out. I'll scan the screen again.
Okay, sir.
Okay, so I showed this table, right? So you hear me now?
Yes, sir.
Yes, sir.
Yes,
Yeah.
sir.
So the relaxation time also, the energy increases as you go from top to bottom. The energy that is required to exit the molecule, but the tau decreases. Tau falls to 10 power minus 15 seconds, as I said, for electron spectroscopy, whereas 1 to 100 seconds for NMR spectroscopy. As a result, you can work out the line width, which is actually a measure of uncertainty. Okay, the measure of the uncertainty. So the uncertainty is extremely low for NMR and quite very high for techniques like rotational, vibrational, uh, electronic, and mass power. Okay, so those spectroscopy techniques which use high energy have low resolution. Those which use low energy have very high resolution. I think this is a very good uh, point to start this lecture. I think stop this lecture because then I'll have to actually talk a bit more on this tau a bit more. I have talked about two of the lifetimes, two of the times are not lifetimes. Time one is the interaction time. Okay, this portion I covered. This one I have covered, and I talked to you what is tau, what is delta E, and what is the line width. So probably today you have learned, I think, why lines are either sharp or broad, how it varies with the energy of the radiation. I think that's a good point to stop. So maybe I think I can come out of the presentation and just talk to you a few minutes by closing this share screen. If there are a few questions, I will take up a few minutes before I just close it. If there are any questions, uh, I especially want to hear from you people whether there's too much of repetition of what you already know, because I need to make a kind of because there are PhD students who have just joined by after doing masters from other universities and colleges and IITs, and there are 2-year MSc students who joined last year, and there are BS students. I'm just kind of trying to pick up some fundamental concepts across the all spectroscopy techniques, so that once you start solving the problems, we don't really worry about if I make a statement that under NMR time scale, you can't distinguish between the two protons. I think you should know what it is. What am I talking about time scale? Okay, so that's what I'm going to talk about in the next class. These, although we say there's a lifetime of the excited states for NMR, which is in the order of 1 second to 100 seconds, even in NMR we see broad signals. Not all NMR signals are very sharp. So that's what I'm going to talk about. Sub-processes, not sub-processes. Protons exchanging their position between a nitrogen and oxygen, or cis transisomers taking place. What are the speed of these processes, and how do they affect the line width? The excited state may be long-lived, but there are other parallel processes, which will broaden the signals. So that's what I'm going to talk about it. So I want to talk to you people about a couple of other things. Those of you taken spectroscopy course, the theoretical part from Professor Datta, Anindya Datta, might have done a bit of group theory. I want you to send in the WhatsApp group how many of you do not have any exposure to group theory at all. I just need to know the number, okay? Because when I switch over to IR spectroscopy from the introductory class, I will need some background information on group theory to be known to all of you before, okay? Otherwise, I'll have to reformat my lectures, okay? So that's one thing. Second thing is that I haven't thought about this, this examination business. There's so much being talked about exams, and I'm busy with so many other things. I have not really thought about exams. And most probably, Suvan Kulkarni told me that I think he used to give at the end of every lecture a quiz in the multiple choice, which I can try from next lecture. Only today I came to know about that he gives 3 questions at the end of every lecture, and you answer this and you have some weightage for that. I'm not sure how much that will work for my style of teaching. Okay, my style of teaching is more of concept based, and then I'm going to explain this. Still, I try to pick up a few questions and have some quizzes at the end of the lectures, and see what I can do at the end of the 3rd week or 4th week, whether I can give only one exam for the entire portion and be done with it. So right now, I'm not talking anything about the exam or quizzes, at least for this week. The last point before I sign off is that Thursday, I am logged in a meeting with the ministry whole morning, whole day. I mean, Thursday, Friday, Wednesday, Thursday, Friday, all 3 days I'm logged. Suppose if the ministry gives me an hour to escape from the meeting, I will come and teach at Thursday at 2 o'clock. Otherwise, is Saturday, 2 o'clock okay for you people? I want to know. So this can be discussed offline in the WhatsApp group, okay? Thursday, 2 o'clock. I'm going to ask those people to let me off. It is a funding related meeting, 20 of us in the group discussing about various people's projects. So if one person misses the meeting, normally nothing should happen big. But in case they insist on me being with them, I will not be able to take the class at 2 o'clock. In which case I want to schedule it on Saturday at 2 o'clock or 2:33, it doesn't matter. We are flexible on Saturday afternoon at any time. So these are the questions we'll take up. We can discuss any doubts about the lecture in 2 ways. One is at WhatsApp for quick questions. I also know that you can upload the notes and the slides into the MS Teams. I will try and do it, but I still prefer Moodle. I think, as you see, my first message to all of you was through Moodle. Okay, because Moodle is something will be 10 years later also it will be there. Even after 10 years, whatever material I sent to you will still be available to me. I can go back and bring it back. Because MS Teams, we may stop teaching next year and next year, but Moodle will be with us. So I will make notes available both through Moodle as well as to MS Teams. I don't think it's a big issue. And hopefully Gargi has recorded this lecture. And any of you are highly computer savvy can split this video into smaller videos and then make it available in the same MS Teams. Gargi, you can maybe take help of hers or someone, or Ashi, one of these class representatives. You can take their help how to split this video. I can do this. Actually, I can do this, but I don't think I really have time for this now. This week is a kind of a really packed week for me. So please do this. And if there are any questions, I will take it up. It is only 3:20. Next 5 minutes, I leave it open the floor for any of you to unmute and ask me any questions. I have a question before. What is the strength of a class? No one knows. 73 are in the classroom right now. 73 are attending, but I thought it's 90 plus I saw in the Moodle. Okay, doesn't matter. So please let me know, give me some feedback on the, the speed at which I deliver and the quality of the video, audio. I do not know about the internet related issues, the voice getting, dragged or gobbled up. But even the delivery speed, I think you can comment on it, because I tend to speak fast. I think those of you who have taken my course before, you know this. But I try to be consciously slow, but may not be slow enough for you guys. Please let me know on that. And then please raise questions related to the chemistry subject, what is taught today. Anything is unclear. And by the way, I think I forgot to tell you this. I think I'm following the book. I'll just show you in the screen. This is the book, the mirror image, Structural Methods in Inorganic Chemistry by Ebsworth, father of NMR spectroscopy for inorganic compounds from University of Edinburgh. He's a professor in Edinburgh who's retired now. I think his student has now published a newer version of this book, which has a slightly different title, which is called Structural Methods in Molecular Inorganic Chemistry. Whatever I essentially spoke is the introductory chapter or the preface of the book. Okay, whatever I spoke today. It is available. I saw in various, websites which are illegally hosting the books. I cannot give you, officially those sites, but I think you can search and download it yourself if you want. Okay, the book is available, so you don't have to look for a. I will not stray away from this book this time. Only 6 lectures. I will only stick to the examples from this book. Okay, so if I expect some interaction from you guys, at least from the next class. I know unmuting and talking is an effort, and then sometimes creates a lot of background noise. But I'm more of a teacher, who go, whose flow is determined by the response from the class. At least the BS students should know that I have taught you 2 years now. Okay, two courses already. So please, be a little bit, in between. Please stop me and then ask me some questions. I do not mind like others. I don't mind any number of interruptions because I repeat what I told you in 438. There is nothing called a syllabus which I have to complete. I can draw the curtain at any point of time and say that's enough. You have learned enough. With the rest you can go. My job is to take you to the pond and you are going to drink. Okay, and you are going to consume the matter. So please ask me questions. Whatever I say should be understood by you guys. With this, I'm just signing off. Take care. Okay. See you on Thursday or Saturday as what we decide on the offline discussion. Bye bye. Take care.
Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.
Thank you.
Thank you,
Thank you, sir.
Thank you, sir.